Hi, my name is Jingyi. I'm the first author and presenter for the paper Iterative Design and Prototyping of Computer Vision Mediated Remote-Sighted Assistance. I completed this work with the help of my colleagues at Penn State. Remote Sighted Assistance, or RSA in short, is a navigational aid for people with visual impairments, where they use a smartphone app to call a remote-sighted person while sharing their live camera feed. The remote-sighted person or agent interprets the live camera feed and provides navigational assistance to the user by natural conversations. Aura and Be My Eyes are two prime example RSA services. Let's watch a short video from Aura to better understand the RSA system.
Hi Juan, thanks for calling Ira. This is Erin.
Hi Erin. I'm at Kellogg Park in La Jolla Shores. I need to get to the corner bakery.
Looks like the closest corner bakery to you is on La Jolla Village Drive. Does that sound familiar?
That's it.
We made 3 contributions in this work. First, we designed different prototypes on how to use computer vision techniques to assist remote-sighted agents so that they can assist users with visual impairments better. This is important because providing RSA service is mentally demanding and stressful for the agents. Additionally, agents' tasks have grown broader and more complex, so supporting them with technologies like computer vision can improve the overall quality of service. Second, we find the desirability and feasibility of our design by engaging domain experts and had them review our design. Third, we discovered key themes and identified design specifications to implement a computer vision mediated RSA service in the future. In previous work, Lee et al. Published a paper at IUI 2022 focusing on navigation challenges during RSA, such as difficulty in reading signage and text in the user's camera feed, difficulty in detecting and tracking moving objects, lack of indoor maps, unable to localize users on map in real time, and difficulty in orienting users in their current surroundings. Some of these challenges can be mitigated with computer vision capabilities. So, for example, text recognition and object detection can mitigate the first 2 challenges. Recently, researchers are exploring the potential of smartphone built-in augmented reality frameworks in indoor navigation, which can mitigate the last 3 challenges. So we formulated this study around the research question, how to incorporate computer vision to support sighted agents in current remote sighted assistance services, and what issues may arise when the agent and users with visual impairments work together through such a system. To answer these questions, we adopted the scenario-based design in this paper and contextualized our design ideas in 5 real-world scenarios. They are walk in the park, airport navigation, office building navigation, navigate from parking lot. One of our initial scenarios, find rideshare, was replaced by grocery store shopping through discussion during Study 1. We proposed low-fidelity pictorial prototypes for each scenario. In this paper, we adopted Aura service as our research platform, which is an RSA subscription service for users with visual impairments. We conducted 2 studies to collect feedback from an RSA domain expert in Study 1 and 12 RSA agents in Study 2. All participants are from Aura. We conducted 13 interviews in total, all remote. Here are some example design scenarios. Here are 2 example prototypes. The left one is a prototype of landmark recognition and syntax reading in airport navigation. The right one is a prototype for office building navigation, including the design idea of showing distance grids, annotations, direction, and object recognition. The top toolbar in each figure shows buttons to toggle a design feature on or off. The left one is a prototype for walking the park, and the right one is a prototype for navigating from parking lot. We ended up with 6 high-level issues describing the relationship between RSA practice and our design ideas, and 5 of them are solidified in Study 2. 1. Reducing the agent's cognitive load. 2. Enhancing the agent's ability to stay ahead. 3. Contextualizing object detection. 4. Emphasizing the people with visual impairments video feed. 5. Managing risk in navigation, as well as managing external factors in Study 1 only. I cannot go into all of them in this presentation, but I will look more closely at contextualizing object detection. For the full themes and findings, please see our paper. Within the theme of contextualizing object detection, we include several concrete suggestions our participants gave us. For example, in Study 1, quote, some types of obstacles are more important than others because the person is more likely to be looking to use that thing. So, for example, a trash can. I do have to have the person move the camera around looking for a tower-shaped object, and sometimes I miss it. So then we have to go all the way back around again. So being able to identify maybe a hierarchy of objects will be very helpful versus having all objects available all the time. End quote. The theme of contextualizing object detections is solidified in Study 2 under the sub-theme of selective pedestrian, object, and obstacle detection, and is shown in this quote. If you have like 20 people, it will be people, and then it will be like just cloud your view through navigation. End quote. This agent was concerned that the feature of object or pedestrian detection will overwhelm her and overpopulate the video feed in busy locations. This brings us to one of the key topics we discussed in the paper, opportunities for computer vision algorithms in RSA. Also, see our written discussion for more details. Which objects are of interest depends heavily on the scenario, context, and people with visual impairments preferences, and labeling all visible objects can result in information overload. While the association with people with visual impairments profiles may help, each of ARA's visually impaired users has a profile that agents can access, containing RSA preferences, such as preference for more or less scenery description when navigating. It would be laborious to specify one's preference for a large range of possible activities. Thus, it is desirable to learn such information on the fly as we deploy systems in real-world applications. To this end, AI can be employed to automatically adjust the importance of features for each agent and people with visual impairments. Further, AI can be used to mine frequent patterns in user data and recommend additional objects to discover, similar to systems that recommend products based on a customer's shopping history. In this work, we developed low-fidelity pictorial prototypes showing case potential applications for computer vision to support RSA interactions and identify the feasibility and desirability of computer vision-mediated remote sighted assistance. And that's it. Thank you again to ARA, NIH, my CIL labmates and advisors, and to our reviewers. For more details, please read the paper, Iterative Design and Prototyping of Computer Vision Mediated Remote Sighted Assistance. And thank you all so much for listening.